Hello, my name is Kosei Maeda. My research is titled Visible Light Communication Ground Test Visibility Results and Proposal for the HIRO satellite. Background. In large-scale emergencies, such as natural disasters, millions of simultaneous connections can overload the wavelength of radiation used for communication, preventing messages and calls from going through. The affected will have trouble contacting their families, and rescue attempts may be thwarted. The issue is the limited bandwidth allocated to the civilian communication and the physical limitation of today's widely used radio frequency-based systems. The main focus of this presentation will be visible light communication, or VLC for short. This is a wireless communication method that utilizes visible light or other short wavelength electromagnetic radiation. Although this technology is mostly implemented indoors today, development in research has shown its potential to be used in satellite applications and can act as a backup plan when current radio frequency-based communications fail. This is a simplified explanation of the visible light communication, or VLC system. A satellite carrying high-power LEDs will send a signal to an observing receiver on Earth using its own unique signaling method, such as Morse code or binary. The receiving end consists of a telescope, an optical filter to cut out any unnecessary noise, and a light sensor, such as a photomultiplier tube or a photodiode. Most advanced systems will adopt a photomultiplier tube as it is able to pick up the slightest signals that it has been calibrated to, although it requires careful tuning and noise reduction. This system is then connected to a computer with, at times, a signal amplifier in between, where signals are then decoded and stored. The main obstacle in VLC is the attenuation of light signal within Earth's atmosphere. From orbit, the visible light signal will travel through the effects of the thermosphere, mesosphere, stratosphere, and troposphere. The attenuation of light occurs mostly in two mechanisms: absorption and scattering. Light absorption occurs when molecules or particles in the air absorb the beam's energy, converting it into heat and weakening the signal. Ozone, nitrogen dioxide, and water vapor are some of the main causes of this. On the other hand, light scattering occurs when the beam is redirected by aerosol or other air molecules without changing its wavelength, but sending the light into different directions and weakening the signal. Now, our satellite, the HIRO satellite, is a 3U CubeSat with basic VLC capabilities. It is designed to orbit the Earth at 500 km altitude in a sun-synchronous orbit, with it returning to the same position on Earth every 5 days. It uses strong magnets and a stabilizer to minimize wobble and guarantee that at least one face of the satellite is facing the Earth. The emitted signal will be received by a highly sensitive sensor, such as a photomultiplier tube, with a bandpass filter and a telescope attached to reduce noise and maximize signal strength. Due to the Earth's magnetic field above Japan being approximately 56 degrees, observation of the satellite will be slightly north of the observer. This satellite is planned to launch on the Space One's Kairos 3 rocket. For this test, we aim to evaluate the feasibility of conducting future observations over long distances. We performed a controlled experiment across a 10-kilometer baseline, from Enoshima to Chojigasaki Beach. This location was chosen as most of the light's path was above water, making the beam having to go through intense water vapor environment. This creates a harsher environment for the VLC system than it would be compared to the expected orbital observation, providing a conservative estimate of the system performance. An LED array identical to the one implemented on the satellite was deployed as the light source, and a camera telescope system was set up at the receiving location. This test allowed us to assess whether our detection setup is capable of reliably capturing the signal over the distance. Now, as seen in Figure 11 and Figure 12, the LED emission appeared as a distinct and stable light source through the telescope under nighttime conditions, even over the water vapor. A second test, a short distance photodiode test, was conducted to evaluate the intensity and stability of the optical signal over short ranges. with results later extrapolated to longer distances. The LED configuration was the same as the long-distance test. To obtain quantitative data rather than photographic measurements, a photodiode was employed in place of a camera. From figure 15, as distance increased, the measured voltage proportional to the received light intensity decreased substantially. Between 1 meter and 20 meters, the voltage dropped from approximately 4.1 to 0.38 volts. This measurement resembles the relationship between received signal and intensity and distance. This measurement resembled the relationship between received signal intensity and distance, consistent with the inverse square law. Between 1 meter and 20 meters, the signal decreased from 4.12 volts to 0.38 volts, closely matching the expected geometric spreading of light from a point source. This confirms that the LED array emits sufficient optical power for detection, even after accounting for distance-based attenuation. Now, minor deviations at longer ranges, but beyond 10 meters, are attributed to minor alignment issues and limitations in the photodiode sensitivity, which I plan to fix in future tests. The results from these two tests show the potential of optical communication at short distances. This needs to be applied to a low Earth orbit environment, 5 kilometers in the case of HIRO, so obtaining light attenuation data at long distances through constant air mass increases data accuracy. By improving LEDs and sensor alignment, we can conduct more accurate experiments showcasing the reliability of VLC signals in orbital environments. Now, with the right development, this technology can be implemented in disaster-stricken regions as a backup channel for civilian and rescue communications, potentially connecting and saving lives. As for future work, I plan to conduct long-distance LED tests using a photodiode instead of a camera to obtain data representing the relationship of distance and drop of signal strength over 10 kilometers and further. To improve the detection of LED signal, we are planning on making the use of parabolic reflectors to improve the intensity of the beam. Furthermore, testing will be carried out in longer distance scenarios, from 10 kilometers, 20 kilometers, and maybe even 30 kilometers. Thank you for listening.